So our next topic is beyond subsidies, creating competitive clean energy solutions by rethinking design and delivery. A very thought-provoking topic. Today we're pleased to have Keith McGowan here, who is a seasoned capital project executive with over 25 years of global experience delivering complex, high-value projects across the energy sector. He's held senior leadership roles at major oil and gas companies, overseeing multi-billion-dollar portfolios in upstream and energy transition sectors. His expertise spans strategy development, project governance, supply chain optimization, and integration of commercial and technical teams to drive capital efficiency and performance. Keith's a recognized industry thought leader with a passion for project performance improvement and currently serves on the executive board for the ECC Association. James, who's another guy that needs a little introduction to the PPI crowd. He's the Chief Technical Officer for Strategic Project Solutions and a member of the Technical Committee for the Project Production Institute. He's been leading research and development of project production management and his underlying framework of operations science, knowledge, processes, and systems to support implementation of large capital projects since 2001. He's one of those top PPM authorities in the world. So we got two really high-class guys here. I'll turn it over to you.
Thanks, Gary. Appreciate that. So I'll get us kicked off with, I guess, why did we write the paper? As Gary said, I've been working on major capital projects in the energy sector for over 25 years. But the last couple of years, I've been working on clean energy projects. And what I noticed was, as I was applying the oil and gas mentality and way of working for major capital projects, but that really wasn't going to deliver the right answer in clean energy projects. And this is really the genesis of how this paper came about. And I was grateful for James to co-write this with me. So I guess we need to look at what are the clean energy challenges, and I think it's really important to understand some of the issues that I saw. So when I looked at oil and gas, and what we had done, and I think Todd mentioned this earlier, typically use the capital value process. It's very much weighted on technical complexity, front-end loading of projects, and working your way through that stage gate until you get into FID and execute. And that was the process that I was using for the clean energy projects I was working on. So front-end loading, really kind of looking at it. But one of the big bits that jumped out at me was, these projects are ultra low margin. You're talking about, 10% IRR at best. And you really don't have, any space to be able to deal with any kind of cost or schedule growth. But you're also looking at, fundamentally different projects as well. The clean energy projects, they tend to be technically simple and actually commercially very difficult. When you start looking at there's subsidies tend to be involved, which then takes you into political cycles. Most of them are project financed through private equity. And private equity are looking for high return on investment. It's nascent industries, and actually the market that you're selling into, it's not established. There's a little bit of chicken and egg going on about do you build it and people will then start buying your product, or do you need the long-term sales agreements in order to actually define what you're going to build? When you're using project financing, the private equity firms, they really want long-term contracts in place so they actually know that they're going to get return on their investment. So it was really tricky about where we were going. Then when you started looking at technology, the supply chain, the technology was there, but it wasn't there, and it wasn't able to be scaled up. It was kind of more standalone type technology, rather than looking at hundreds and hundreds of megawatts moving up into gigawatts of scale that we were looking at. So there was a technology gap, and then when you looked at the supply chain, the supply chain is dominated, certainly for green hydrogen. I was working on over in the kind of China Far East area, and that started bringing in lots of geopolitical issues about where you can buy stuff. When you start looking at government subsidies, lots of them tie in about how much local content do you need to have in each of the different projects, again further complicating where you can buy your equipment from. I guess, you kind of sit back and go, well, why bother? It seems really difficult. It's ultra low margin projects. You got high amounts of risk, high amounts of complexity. There's no market in place. So, really, why are we doing it? Well, I guess, the energy transition, it has to happen. It's going to happen, and it's just about how do you get there. So, when we looked at this paper, it was, we need to come up with a new delivery system. We need to come up with a new way of thinking if we're actually going to be able to build clean energy, that solutions that actually make sense and are competitive in the energy mix. So what's the transformation that we're talking about? It's really kind of coming down to combining first principles thinking with project production management. And when I was looking at why this, when you kind of think about first principles thinking, like I say, that there's lots of bias, there's lots of constraints, there's lots of this is the way it's always been done. But what we do know and what I'd learned, over the last few years was that that thinking isn't going to give us the right answer. It'll be incremental little steps, towards something, but ultimately it's going to continue to be very expensive. And when you look at the cost of green hydrogen versus fossil fuel hydrogen, you know it's about $1.50 per kilo for fossil fuel hydrogen. It's about $10, $8 a kilo for green hydrogen. So you need something radically different if you're actually going to be able to come up with a competitive solution. So first principles thinking was one of the key concepts that we kind of landed on. You need to be able to break down the challenges into the fundamental truths. It's not new thinking. It's been about since Aristotle, right? And actually it's been used in various elements of business. I guess probably the most famous one lately is Elon Musk. He kind of talks about boiling everything down until you hit the fundamental truths and then reasoning up from there. Why does that help? It really kind of helps with removing the bias, trying to come up and very clearly articulate what's the goals and the outcomes you're trying to achieve, and when, and why are they important? So then you can really start thinking about, well, how are you going to solve that answer? When you then combine that with project production management, I'll hand that one to James.
Yeah, thanks, Keith. So one of the things that we actually need to really understand is the slide that was actually that Keith actually had described a little bit, and that is working on actually optimizing the energy production system as well as the actual project production system that allows that to be built or deployed. Okay. So the question is, we actually see many times where working with project delivery teams, they actually say, we are working on really efficiently building a wrong project. Right? So therefore, it is not only important to understand project production systems, but also the actual production system in which the energy is going to get created when we're actually looking at this new energy, clean energy solutions. So I'm not going to actually go over this concept. Again, Keith actually has already talked about the benefits of having first principles thinking. And Todd and Roberto and Lon actually has already talked about project production management. So again, the core concept, looking at project as production system and applying operation science and fit for purpose design and autonomous technologies with sufficient benefits that have proven that there is something here. Now, one thing that's really interesting is a lot of people through the Project Production Institute know that this type of thinking applies to projects. However, the PPM OS is applicable to any production system, whether that's truly pure manufacturing systems like continuous flow, line flow, batch flow, job shop, supply chain, or engineering, fabrication, logistics, on-site installation, and commissioning. Now, how can we say that? Because it's not something that is theoretically possible, but things that has been applied and has delivered substantial results. So let me actually take one example, just one sector called data centers, which probably is where majority of the dollars or capitals are being spent right now. One, we actually worked on the lead time reduction for hard disk manufacturing. Okay. Two, inventory optimization for data centers, including hard disk and other equipment that go in for the operation of that data center. Three, lead time reduction for fabrication of electric modules. Four, capacity analysis of the supplier for the electrical modules. Five, synchronization of equipment, fabrication, delivery, and installation with the building of the data centers. Six, engineering, procurement, construction, and commissioning the predictability and schedule optimization for engineering, procurement, and construction and commissioning of data centers. And then, last but not least, is the resource optimization of the owner-operators that are going to be leasing multiple, many data centers around the globe. So again, as you can see, for just one vertical, you can actually see that this type of thinking applies to any type of production system. So when we're actually looking at the renewable energy or clean energy, one of the things that we want to actually do is to actually look at the actual production system where the output is the energy itself, and then the project production system where the output is the project itself, the facility itself. Okay. So by combining the two approaches, the first principles thinking with PPM, what we're able to do is actually say first principles thinking actually brings structured approach to remove biases, come up with the original solutions, and assist with better decision making. Whereas in project production management / operations science brings the framework to describe behaviors of production systems and variables that drive those behaviors, right? Because it's really, how do we simply describe the behaviors and what variables do we actually use to describe those behaviors is very important. Second, methodology to qualitatively and quantitatively analyze trade-offs between these design decisions. Again, it could be the actual energy production system or project production system. And then third, as Todd actually already talked about, approaching for controlling production system to achieve the desired behavior. And then number four, most importantly, is these are not just the concepts and ideas, but there are tools to enable sustainable and scalable implementation. So again, bringing those together could actually be applied to any type of environment. But what we're going to try to do now is Keith is going to actually take this and apply to green hydrogen. Keith?
Yeah, thanks, James. So I think it's important to start with, what are some of the fundamentals of hydrogen? So gray hydrogen, that's what's been used for decades. So that's generation of hydrogen from fossil fuels, natural gas, CO2 is emitted. As we go into the energy transition, so blue hydrogen, green hydrogen were two of the colors that were added. So blue is using natural gas, but you're capturing the CO2 and storing it in aquifers, underground caverns, etc. So that's carbon neutral. And then green hydrogen, which was the area that I was working in, specifically using renewable clean energy with water, using electrolysis, to split the hydrogen and oxygen apart. You capture the hydrogen, oxygen, and there's an awful lot of heat generated in this, so they tend to be vented and not captured. So we will focus on green hydrogen as we go through this. So what's some of the challenges of green hydrogen? I think the first bit to understand is that, levelized cost of hydrogen, or what's the cost per kilogram. And I mentioned this a little bit earlier. Gray hydrogen is about $1.50 a kilo. Green is somewhere between $8 and $10 a kilo. If you then start looking at subsidies that are available, so if you look at the Inflation Reduction Act, you can get up to $3 a kilo subsidy on your product of green hydrogen, but that still doesn't close the gap. You can also look at potential. Some governments are looking at carbon taxing, etc. For grey versus green, but either way, it still remains expensive and uncompetitive. So who's going to pay the premium? Should people be paying the premium, or should we be looking at different answers and different solutions to try and drive that cost down and get it as close, if not on parity, with grey? When you look at they are commercially complex. As I mentioned, subsidies are difficult. You're spanning multiple political cycles just for the duration, of the projects. When you start spanning political cycles, that means your subsidies, have the potential to change. So, trying to get away and not be reliant on subsidies in order to be profitable is really important. The technology as it stands, green hydrogen technology has been about for ages, but most of the electrolyzers that are available, they're quite small in size. They're like 5 megawatts. I think the biggest is probably about 20 megawatts. When you're trying to build plants that are 100, 200 megawatts, going up into gigawatts with that type of technology, you're starting to have to string lots of these together, which adds in complexity. On top of that, as they've been designed as standalone units, each of the electrolyzers, they have their own separators for hydrogen and oxygen. They have their own cooling system. They have their own control systems, water polishing systems. So when you start adding multiples of these, you start getting, too many parts. They haven't been designed for scaling up. And I think that's one of the fundamental bits that needs to change, is about, how are these things packaged, and, and actually coming up with a design that is suitable for industrial scale. And then lastly, when you look at efficiency, as I mentioned, an awful lot of heat is produced, when you're doing electrolysis. So, about electrolyzers, they're about 60% efficient. Efficiency is king in this. Over 50% of your cost is in electricity. And when you're losing 40%, roughly on heat and, byproducts, you're starting to lose an awful lot of value, right? And you're not able to do anything with that. But when you look at, the fundamental truths of green hydrogen, the energy has to be carbon free. Now that can be wind, solar, nuclear, hydro, geothermal, doesn't matter, as long as it's carbon free energy. You then have to have a transmission system, take the electricity from where it's being generated to where the plant is. These plants tend to be close to the consumers because hydrogen is quite difficult to move. So, you have to have that transmission system in place. And it's kind of well known that the transmission systems in many of the countries probably isn't suitable for the additional capacity that needs getting added on. The electrolysis, say it's about 60% efficient. There are some companies that are working to try and, increase efficiency, up into the 80%. But, is that good enough? Or is there, do we need to continue to push the boundaries on that? Electrolysis itself has to have, very clean deionized water. So, water is your feedstock. Again, depending on where you're doing it, water can be a restriction, just due to availability on there. So, that's an important bit to look at. Once you then get the hydrogen, and you split it out through electrolysis, you have to be able to do something with it. So you're either going to be, compressing it and storing it. You're going to be turning it into a different, more, easily to transport molecule like ammonia, methane, methanol. But like I say, you've got lots of heat, you've got lots of oxygen at the minute, and I don't know if these are fundamental truths, but it said the outputs must be captured, stored, and transported. I think at the minute they're not. They're vented. It's just lost. I think if you're looking at the competitiveness and how do you actually drive and improve value, those outputs should be considered as you need to do something with them. And then, like I say, you go into, where do you want to use it? So are you going to transport it? Are you going to burn it in factories or whatever? So that's the fundamental truth that we've seen. When you then move on to operations science, James.
Yeah, so what we actually have done is taking the diagram that you actually saw and turned it into production system map that starts from your electricity sources and water sources. And as Keith actually just talked about, there is the process to generate electricity, transform electricity, and transport electricity transmit the electricity to the performing of the electrolysis, and then you actually have the water. Again, the water has to be treated and transported, and then it actually gets through the electrolysis, it gets separated, and then the heat is also created, and heat actually cannot be stored on its own. So it actually has to be captured into a medium, whether it's air or liquid, and then that actually has to be transported and consumed. Whereas the same thing actually has to be done for the O2 and H2. It actually has to be captured, transported to the actual consumers, the various consumers that Keith already talked about. And what's interesting is this is the same concept and discussion that we've been having this morning. How do we actually determine what to do where and how, and optimize the overall system, right? So again, the concepts that Todd talked about, production system optimization, production control, and CAPE all start to actually come into play, and when we're actually looking at it from the overall optimization. And as Keith said, it's just actually optimizing a single portion or side of the approach is not working. Okay, so once that actually is done, you actually have to figure out how you're going to deploy this. Again, these technologies are not meant to be a single project and forgotten. Okay, so the question becomes whether this is, again, any type of project that is going to get deployed. A lot of people think, and we talked about this in past conferences, is a lot of people actually think once we actually have this manufacturing approach adopted and manufacture, it will automatically somehow get deployed or simply get deployed. But what we're finding is that's not true. Okay, the reality is a little bit more complicated because the demand and local requirements and conditions of each site requires configured to order installation. So not only the solutions actually have to get somewhat standardized in order to increase efficiency, but they must actually have ability to be configured so that they are adaptable for any type of environment that you wish to actually put this onto. So that actually now brings the actual production system where the output might be a facility. Again, as Keith actually said, all the icons shown on the right may be in various different locations. So again, what to do where and how as a system comes into play when we're actually working on the actual production system for energy, as well as the actual production system for the facility itself. Okay, Keith?
Yeah. So when you start looking at clean energy, and like I say, these projects, they're complex, they span over multiple years. But when you talk about clean energy, most people default to solar and wind. But there's lots of different types of clean energy out there. And when you think about solar and wind, as the typical go-tos for clean energy, they're inefficient and they're intermittent. And if you want to optimize the output of a green hydrogen facility, it needs 24-hour reliable, dispatchable power available, because that's how the electrolyzers work at their optimum level. When you're dealing with something that's 60% efficient to start with, you don't want to degrade that further because you're going to be leaking lots of value. So you really then start coming down to how do you make clean energy 24-hour dispatchable, reliable energy source? Because at the minute it's not. And it's not without, adding in batteries, right? But when you start looking at battery energy systems, again, most people start thinking about battery energy systems as lithium-ion batteries. So these projects need solutions, and when you look at the cost difference in, the cost of hydrogen, you have to get rid of rare earth metals, you have to increase the efficiency of these things, and you have to have energy, which is competitive. And at the minute, if you're buying, reliable 24-hour clean energy from a grid, it's not competitive, it's really expensive. So, you're starting from a losing position if you're there. So, how do you get to that clean energy solution, which is giving you what you need, but in a competitive way? And this is where you need to start rethinking about, what is an energy system? So, we need to move away from thinking about silos of solar or wind and start thinking them as hybrid systems that, work in a symbiotic relationship. So, for example, can we think about, a big nuclear plant that has to run, and nuclear plants just like to run at one level? Can that be used, at night to power a green hydrogen facility when demand's low? And then solar takes over through the day when the demand on the power from the community is going to be higher on the nuclear facility. That would help you, reduce the amount of batteries that are needed, in order, because they're working together. When you then start looking at batteries, and there's some interesting battery developments out there. But one of the companies that I was looking at is Rondo Energy, for example. So they've taken batteries, and instead of looking at lithium ion and storing like sunlight as electricity or ions, they're looking at it as thermal energy. So they're using bricks, and basically putting them in what you could describe as a very large toaster oven. So you're using the solar to heat up the elements of the toaster oven that's heating your bricks up, and these get to incredibly high temperatures. And then they're using the heat that's stored in the bricks in order to generate steam, in order to deliver electricity. Again, they've taken something which the industry was going down a certain line, and they're looking at it in a very different way. And there's other companies that are doing similar and challenging what is a battery. Another interesting company that I came across was, I always thought that hydroelectric was determined by geology, and geography, because that's kind of what you need. There's companies out there that are actually starting to rethink, hydroelectricity and being able to put it wherever you want. And that's by using, purpose-built caverns, etc. There's some interesting, challenging ideas out there, which I think is going to help answer this question of clean energy and intermittency, and and make it competitive. So I think the more that the technology develops, it's going to really help the green hydrogen industry. But moving on from that, there's a big what if for me. When you look at current thinking, would suggest it's basically green hydrogen, green ammonia must be done onshore, right? It's got to be onshore because that's kind of what the technology states. But why, right? Let's challenge about why should it be onshore, and can you take green hydrogen, green ammonia, and put it offshore and put it subsea? Now, I've had this conversation with a few people, and most have laughed at me, when I've kind of said this, because they went, "That's crazy. Why are you thinking about that?" But really, when you kind of cast your mind back, oil and gas started in the desert. But when you start looking at the evolution of oil and gas, it moved offshore, it went subsea, and that was to access better acreage, better fields, and open up different frontiers. So why can green hydrogen and green ammonia not follow a similar path? So let's look at the offshore and subsea piece in a bit more detail. Some of the big issues that the hydrogen has, or green hydrogen has. You've got to, if you're going to store it, you're storing it at high pressure. Essentially, the big concern is explosion risk once you start, dealing with, high pressure hydrogen. So, that then starts dictating on land. It can't be near communities. It's got to be, out of the way. So, that starts limiting where you're at. When you then start thinking about, solar, wind, clean energy, you don't tend to find those the most natural places and the optimized places for those right beside where you want to actually have your production facility. So like I say, that starts bringing in large transmission networks and systems, adding more complexity, more expense in there. I've mentioned the heat. There's lots of heat produced. So, when you're on land, that means you really need to start, building big complex, cooling systems in order to deal with the heat. You have to have the electrolyzers, inside buildings, right? The buildings have to be explosion proof. They have to have lots of fire and gas sensors, etc. Those buildings are expensive, right? And the more units you have, the more buildings you're going to need. So that, when you start looking at the issues that are sitting in front of you, does offshore and does subsea start answering and start, helping actually eliminate some of those issues? Well, yeah, if you go offshore, you don't have to worry about the public, because there's nobody there. When you start putting the electrolyzers subsea, and the production of the, hydrogen and storage, of compressed hydrogen subsea, you don't have explosion risks. The seabed temperature is naturally about 4 degrees C. So you've got, a natural heat sink that sits out around it. So you don't need cooling. You don't need buildings because you don't have the explosion capability. When you then start, thinking, well, I can put that right beside a wind farm. So now you're getting rid of the transmission losses, the big transmission issues that you've got. And then if you actually have, floating ammonia production sitting above it, similar to an FPSO that was used in oil and gas, that starts getting everything in one area, quite neat, tidy package. So the main concerns about doing this is, people start talking about construction and maintenance costs, and it's just really expensive when you go offshore and you go subsea. Yeah, it is, right? But you need to start weighing that against everything else, what are you taking out of the system versus the cost of actually having vessels. When you then start looking at the electrolyzers, yeah, it's new technology. There isn't electrolyzers that are, commercially ready to be subsea, but there are people that are working on it. And, the early indications are because you're like working at hydrostatic pressure, it's naturally compressed. You can actually start looking at these, using cheaper materials. Therefore taking the cost of those electrolyzers down. So again, I think it's an emerging place. There are companies that have actually started being offshore with not subsea but offshore. So there's a 200 megawatt green hydrogen facility offshore in China that's operating today, and there's companies like Switch H2 that are actually in the process of designing and building an offshore e-methanol FPSO, for want of a better phrase.
Hey guys, are you about at the end here? We're
Yep.
about at our time. Okay.
Yep.
All right.
So hit your conclusions and then we'll wrap it up.
Yeah.
All right. Sounds good. Yeah. So again, this is a technical conference. Has this been systematically applied together? No, but we believe that there is opportunity to actually do so, where one actually provides a structured approach to question the existing assumptions, and we can the operation science and project production management can enable the purpose-built delivery models. And when it's applied to a clean energy solution, it actually has to be self-sustaining without subsidies. And while the current technology is not scalable, we believe that the innovative thinking can actually bring some solutions that can meet these challenges. Sometimes bold thinking is needed, even if some people think you're crazy. And a lot of, as they say, it's the crazies that change the world. So the next step for us is to identify a project where this approach can be fully implemented. Again, it doesn't actually have to be a clean energy project, and then and document for a case study. So the request out there is anyone interested.
All right. So if you've got an interest, reach out to one of these guys and let's get the ball rolling. I think you laid out a really powerful case for a different approach of first principles thinking connected then with production management, production engineering. Excellent, thought-provoking. I can only imagine how some of your ideas were received within your former employer when you flopped some of those novel concepts out there. Given my past experience, I can only just imagine. So thank you guys very much for your thoughts and your contribution today.